So I'm going to go over the last bit of information related to organic chemistry. So this will be the last new material for our semester. The only thing left after this will be the final exam review. So we're still talking about organic chemistry, and now we want to talk about the concept of functional groups. So we're going to start to talk about molecules with more than just carbon and hydrogen. We're going to integrate stuff like oxygen, nitrogen, etc. into our molecules. So functional groups, this is talking about a specific grouping of atoms with a particular chemical and physical property. Particular chemical and physical properties. So a big part of organic chemistry is classifying compounds by their structure and then being able to say, this is an alcohol. I know all alcohols have high boiling points and all alcohols undergo this type of reaction. That's the general idea of why we want functional groups, so we can classify molecules and say all these molecules are going to behave in a similar way. So we'll talk about, I think, 4 of these. So we'll start with alcohols. And the general notation we have for alcohol is this ROH. And R just represents any generic hydrocarbon chain. It could be 1 carbon, could be 10 carbons, whatever it is, but R is our generic notation. So first, let me remind you about the structure of water, right? When we draw that, it's for the oxygen, it's 2 bonds and 2 lone pairs. So that's our expectation for the behavior of oxygen. And so when we integrate it into a carbon chain, one side still needs to have the H attached, and then the other side will be attached to a carbon chain. So if we start with the smallest one, CH3OH, that will be called methanol. So again, the meth prefix telling me that it's a 1 carbon molecule, and the all ending to tell me that it's an alcohol. So this structure, CH3OH, that's really our simplest alcohol. So if you're looking at what's happening with the oxygen, there you see 2 bonds and 2 non-bonding pairs. So when we start to think about how this is going to work in general, we'll have the carbon chain name to tell us the number of carbons. We'll have the OL ending to tell us it's an alcohol. You drop the E, so butane would make butanol. And then if it's needed, which it usually is, we'll include a number to talk about where it's located. So let's say that we want to make the molecule 1 butanol. So I first recognize that it's going to be a 4 carbon chain because of butane, all to tell me it's an alcohol, and then specifically it's telling me it's on carbon 1. So the way I translate this is first I draw a 4 carbon chain, 2, 3, 4, and then we know it's an alcohol and we want to put an OH group on carbon 1. So 1, 2, 3, 4. I know I almost always number left to right. Theoretically, you can number right to left as well. In reality, you number to minimize the numbering, but that's more complicated than what we need to worry about. So then all I need to do is draw a line off of carbon 1 and attach it to the OH group. I can show the lone pairs on there if I want to, but generally in line angle drawing I don't need to do that. So if that's 1 butanol, then what would 2 butanol look like? Again, same interpretation, right? It's an alcohol, it's 4 carbons because it's butane, and then the alcohol group must be attached on carbon 2. So same strategy, I'll draw my 4 carbons and then just number them again, 1, 2, 3, 4, and then the OH group will go on carbon 2 like this. So that's 2-butanol. What else could we draw? I'll do one more, I guess. What if we had, let's say, 3-hexanol? So now there's hexan to tell me it's a 6-carbon chain, all to tell me it's an alcohol, and then 3 to tell me the location. And now I can draw 6 carbons in a row, 2, 3, 4, 5, 6. And then if I number 1, 2, 3, 4, 5, 6, then it's telling me to put an OH group coming off of carbon 3. So when we're talking about alcohols, these are all polar molecules because the OH group is a polarized bond, since oxygen's so much more electronegative than hydrogen and much more electronegative than carbon. These can participate in hydrogen bonding, which, if you remember, that's the strongest intermolecular force. And because of this strong intermolecular force, these are molecules with relatively high boiling points because they require a lot of energy to break these intermolecular forces. Not the chemical bonds, but the intermolecular forces. Okay, let's go on to another functional group then. Now we can talk about amines. So that was an oxygen-containing functional group. Now we're going to talk about a nitrogen-containing one. So amines, again with my generic R to indicate a hydrocarbon chain. There could be one hydrocarbon chain and two nitrogens or two hydrogens attached to the nitrogen, or 2 carbon chains and 1 hydrogen off the nitrogen, or all carbon chains, just 3 carbon chains, no hydrogen off the nitrogen. So let's start by drawing NH3 again. And so remember, when I draw NH3 with my 8 total valence electrons, the nitrogen gets 3 bonds and 1 non-bonding pair. So whenever we see nitrogen, 3 bonds, 1 lone pair. That's the typical pattern we're expecting to see for a neutral nitrogen atom, which is what we're interested in talking about here. So in this naming scheme, we still use the prefix that indicates the chain length, but because there could be 2 or 3 chain lengths, we'll also see some prefixes like di for 2 and tri for 3. So let's start with this first one, and the name for this one is just propylamine. So this naming scheme is a little bit different, right? All it tells me is propyl, a 3-carbon chain, and then amine. So the way I interpret this is that means there's 3 carbons, 2, 3, and then an NH2 group coming off of that carbon. And you can put the lone pair if you want there, but it's not necessary for the structure. So that nitrogen's attached to 2 hydrogens and 1 carbon, and it has a lone pair, so it's satisfying its valence of 5. And it's telling me about a single propyl group attached to that nitrogen, so that's propylamine. I think that'll make more sense when we do a couple more. Remember I told you we could have prefixes to indicate the number of groups attached. And so this is just telling me about what's directly attached to the nitrogen. So ethyl, amine, and the prefix di. So diethylamine means there are 2 ethyl groups attached to this nitrogen. So here's the nitrogen, 1, 2, 1, 2. And then here's the hydrogen, on that nitrogen. So diethylamine, because there are these two carbon fragments attached to the nitrogen. If there were two different types of hydrocarbon chains attached, that would be possible as well. So I could also have something like ethyl propylamine. And again, beyond the scope of what we're interested in, but when I have groups attached, I list them in alphabetic order. That may sound familiar from the coordination compound naming. So it's ethyl propylamine. So it's a 2-carbon chain and a 3-carbon chain attached to nitrogen. So here's my nitrogen, 1, 2, 1, 2, 3, and then hydrogen in the middle, lone pair if you want to show it. So now it's ethyl, 1, 2, propyl, it's 1, 1, 2, 3. And then we could have an amine with 3 groups. Let's just say we have one with 3 identical groups. I could have something called triethylamine. So here, ethyl and amine, and there's 3 of them. So triethylamine means I have a nitrogen attached to 3 2-carbon chains. 1, 2, 1, 2, 1, 2, and then a non-bonding pair like that. That would be triethylamine. So, right, each of these is a 2-carbon fragment attached to the nitrogen. It still has a lone pair, but notice there's no hydrogen on the nitrogen in this case. So when we talk about amines, they're also polar, and most of them can hydrogen bond. And because they're polar and can hydrogen bond, usually they have a high boiling point. The only thing that's going to be different is the fourth one, triethylamine. That can't participate as a hydrogen bond donor because it doesn't have a hydrogen attached. Okay, let's do one more functional group, and then actually we'll combine 2 of them together to do a last functional group. So now we want to talk about carboxylic acids. And you've actually encountered carboxylic acids before. Acetic acid is a carboxylic acid. And so the general form, you see this RCO2H. So what that means is that these molecules have C double bond O, OH. And since this group is so complicated, this has to be at the end of the chain. So we won't need numbering here to indicate the location. We'll just have to talk about the chain length. So like I said, you've already seen acetic acid. It's a 2-carbon carboxylic acid. And so that's the common name for it, and that's what you typically expect to call it. But the official name for acetic acid is actually ethanoic acid. And so ethan to tell you it's 2 carbons in total, and then oic acid to tell me that it's a carboxylic acid. So then we could just indicate what we're looking at based on carbon chain length. So for example, this molecule with 3 carbons, 1, 2, 3, would be called propanoic acid. And now with the propan prefix telling me it's 3 carbons in total. we could also have, let's say, 5 carbons. One, two, three, 4, 5. So we're including the carboxyl carbon, that's what we call it, the carbon that's attached to the double bonded to the oxygen and the OH. So that one counts. So this would become pentanoic acid. So if we're talking about carboxylic acids, again, these are polar, probably more polar than others. This is going to translate into a high boiling point for the most part. Most of the larger ones are even solids at room temperature, so very high boiling point. And these are acids, right? And what we expect is a pKa range between 3 and 5 for these, right? Acetic acid's around 4.7 something, so pretty typical for most of these. So that's what we'd expect as the pKa value there. So then a fair number of you are probably going to do some biochemistry classes at some point in time, or at least biology classes where you're going to be interested in chemical structure. So we're going to talk a little bit about amino acids. And so we've talked about amines and we've talked about carboxylic acids. So when we talk about amino acids, that's what's coming together in order to make that molecule. So the typical scheme for an amino acid looks like this, where I've got an NH2 group, a carbon in the middle, and then a C double bond O, OH. And generally there's something on that central carbon, that's what we'd call the amino acid side chain, that gives it its particular structure. So that could be anything. It could be as simple as a hydrogen, could be a carbon, it could be anything really that's attached onto that carbon center. That's what makes an amino acid. Well, when we talk about NH4+, that's ammonium, and that has a pKa around 10. And we were just talking about carboxylic acid, and that has a pKa between 3 and 5. So if we think about these amino acids in the conditions they typically exist in, like let's say, just for argument's sake, at a pH of 7, if I'm at a value below pKa, that means the acid is still protonated. If I'm at a value above pKa, that means the group is deprotonated. So normally when we think about the structure of an amino acid at pH 7, the amine is protonated as ammonium, and the carboxyl group is deprotonated as a carboxylate. So you may have talked about what we call the Zwitter ionic form of a molecule, and that just means that there's 2 charged ends, but in this case the molecule is neutral overall. So this is what we call the Zwitter ionic form. So for some examples of typical amino acids, the simplest one is actually just this molecule here, where I'm going to draw these hydrogens in. I know that's not the point, but just to be clear, if the R group is just a hydrogen, then this amino acid is called glycine. And you don't need to memorize these now, but if you have biochemistry in your future, you probably will have to do that then. if this is a CH3 group, just a methyl group, then this is the amino acid alanine. And just to show you how complicated some of the structures can get, this is the amino acid tyrosine. So if you do have to memorize these, which again, if you're going to take biochemistry, you likely will have to, then there are a lot of mnemonics to remember each one of these, but that's what the amino acids look like. And when we're talking about them at pH 7, you expect the nitrogen to be protonated and the oxygen to be deprotonated. So one last thing to say here is we can talk about a polypeptide chain. So normally we're not looking at these things isolated. They're all connected together in order to make a chain. So let me draw one of these neutral. I'm going to draw another one. We'll call this R1. And we'll call this R2. So if we imagine these coming together in order to form a one single molecule, what ends up really happening is we kind of lose water as we put these together, and then we make what's called an amide bond. So if I were to put these together, what I would end up with is a structure like this. And so what we have here is what we call an amide bond. So you're effectively losing the H from the nitrogen and the OH from the from the carboxylic acid in order to make this amide bond. And so I could continue on here, right, and make more of these depending on what we were trying to do. But that's what makes it a polypeptide once there's more than one attached. And if we wanted to go further on, we could, right, if we replace that one, then we could have NH again, and then let's say R3, I guess, and then another C double bond, and then NH again, and then R4, and then let's say that's it, and then we have our terminus. And if we were at pH 7, again, the amine would be ammonium, and the carboxyl would be deprotonated as carboxylate. But that's the way they attach, so you can see between side chains, we end up with these amide bonds, which are really strong bonds, which is good since that's what polypeptides, proteins, etc. are made out of. So we're starting to see this idea of what we call polymers, and we've kind of copied nature to some extent in order to make our own polymers. So we can think about things like polyethylene. And polyethylene, basically what you're doing is taking ethene and doing what we call a polymerization reaction in order to attach a series of ethenes together. And in the simplest sense, you can imagine the polymerization kind of looks like this, where one pi bond swings out to attach to the neighbor, which swings another pi bond out, etc., in order to make connections. So polyethylene is just a really long carbon chain like that. And generally, stuff like polyethylene is used to make really flexible things like plastic bags and bottles. So it just looks like a really long hydrocarbon chain. That's why it's pretty flexible, but also pretty durable. That's why plastics are long-lasting, but that's also why they are hard to break down. Other polymers that we talk about a lot, another one is almost the same, but it's polypropylene. So now, rather than the 2-carbon ethyl, now you see 3-carbon propyl. So now what we end up with is this propyl group instead. So if you model it after what I just showed you, then you could imagine here's a propyl, here's another propyl, like that. Let me draw one more. And so now the pi bonds, in the presence of some catalyst, will start swinging through in order to connect like that. So the net result here will be that every other carbon has a methyl group on it, so a 1-carbon branch. So we could expect that now, let me do one more, then every other carbon is going to have this branch off of it, and that's going to lead to some slightly different properties. These are a bit more rigid, a bit more durable, so we use these for plastic containers, plastic car parts, so more durable but pretty similar in terms of what we're using to make these. So yeah, let me tell you about 2 more polymers, and this is so you get a general idea of how polymers form, but also just for your general knowledge about these materials that are pretty commonly used. I'm not really going to ask you anything about this stuff. So, okay, let's see. So 2 more I said. The next one we can talk about is polyvinyl chloride, which we know better as PVC when you're making water pipes in particular. Bottles are made of it as well. So now here, the molecule that we're going to use, that's what we call vinyl chloride. So now rather than a carbon chain, there's a chlorine. So then polyvinyl chloride will be almost the same, but now it's every other carbon will have a chlorine on it instead, and this gives it substantially different properties. So like I said, typically we expect this for water pipes, so in your plumbing, and there are also plastic bottles that are made of PVC. Those are a little bit less common. Okay, last example here is one you've hopefully heard of, and that's called Teflon. And Teflon's real name is PTFE. Teflon is the proprietary name, and this is polytetrafluoroethylene. So if you're looking at this name, well, poly just means it's a polymer, so that's not telling me a whole lot. But tetrafluoroethylene, that's telling me that there are 4 fluorines per ethene unit. So now what I'm polymerizing is this molecule. So all Teflon is a saturated polymer with fluorines everywhere. So let me draw it a little bit differently here. So imagine that every carbon that's attached has fluorines on it throughout the carbon chain. So what we know Teflon for is its non-stick properties. But we've also recently been told that some of these things are a little bit dangerous because if we're at high enough temperatures, then these coatings can kind of peel off. And that seems to be the case with most non-stick coatings, that eventually they start to peel off. But then while we're talking about it and we see what the structure is, why is Teflon non-stick? And the answer to that is the presence of all these fluorines. So fluorine is substantially more electronegative than carbon. So in each of these carbon-fluorine bonds, there's a tug of war between carbon and fluorine over the electrons that fluorine is winning by a large margin. But now all of these fluorines are competing with other fluorines because there's so many saturating the entire molecule. So what ends up happening is there really is no dipole, even a moderate one, present in this molecule because the fluorines are really having a tug of war with each other. So because the fluorines are really occupied pulling against each other, they don't have the opportunity to create any intermolecular forces, whether it would be with water or something nonpolar like an egg or butter. These are things that just aren't going to stick at all. So the reason Teflon is non-stick is there's no ability for this polytetrafluoroethylene to have intramolecular forces with anything else that's near it. If you put a droplet of water on a Teflon pan, you'll really see that it makes itself into a tight sphere because it can't have any favorable interactions with the Teflon surface. And fatty things like eggs, they're not going to stick at all. All right, so that was kind of a quick dose of all things organic chemistry. I thought it would be helpful for you to talk about amino acids since that's likely to come up in future classes. And since we were talking about polypeptides, I thought it would be just an interesting add-on to tell you a little bit about some of the typical polymers that we use in everyday life. So that's it for this section. All that's left is the final exam review and the final. So hopefully that made good sense. And when you look at the homework and what I actually